On the ocean floor hides more history than the land.
Hides more history than the land.
On fossil evidence of ancient life rests
Fossil
under miles of water.
Ancient life rests under miles of water.
A traditional shallow water digs cannot access this prime record, and we must confront the crushing reality of the deep ocean environment. The new technologies are the only keys to unlocking these ancient secrets. Now that we understand the challenge, let's explore the mapping solutions. A seismic mapping reveals the subsurface geology without drilling a single hole. On acoustic pulses reflect off density changes, creating a geological blueprint. The autonomous underwater vehicles carry these advanced sensors across vast expanses. And these systems map terrain features essential for targeted fossil retrieval sites. Identifying potential fossil-bearing layers remains the crucial next step. Anomalies in density or reflectivity might signal ancient organic remains. But mapping only tells us where to look. We still need to drill. A deep-sea drilling requires immense power and precision anchoring systems. The drill must withstand pressures exceeding 1,000 atmospheres constantly. This process extracts core samples, perfectly preserved columns of Earth's past. Each meter of core represents potentially millions of years of undisturbed history. Paleontologists scrutinize every millimeter for microfossils and chemical signatures. But why seek evidence of early chemosynthetic life existing entirely without sunlight? Now that we understand the drilling methods, let's look at biological targets. Deep cores can capture entire ancient ecosystems preserved in mudstone. But these layers document shifting ocean chemistry across geological timescales. On-isotope analysis reveals past ocean temperatures and carbon cycling rates. This data helps us model how the oceans react to climate shifts. But physical retrieval is still necessary to confirm subsurface findings. The pilot must trust their instruments completely in zero visibility situations. Control interfaces must translate complex robotic actions into intuitive pilot input. But positioning the collection device accurately over a tiny fossil patch is paramount. A new vacuum and suction methods minimize disturbance to fragile specimens. The collected sediment is immediately sealed within pressurized collection chambers. But getting samples back to the surface safely requires controlled ascent rates. The true work begins when the pressure seal is finally broken. Maintaining in situ pressure during initial analysis is a complex logistical feat. But this dedicated infrastructure allows unprecedented access to deep biosphere data. Molecular analysis now searches for ancient biomarkers preserved within the mud matrix. And we might finally find the elusive origins of multicellularity deep below. The deep ocean floor represents geological chapters largely missing from land records. On preserving these unique cores, for future generations of scientists is vital. But the investment in deep-sea exploration pays dividends in fundamental knowledge. Abe future tools will integrate drilling data with real-time biological monitoring. Imagine autonomous probes performing multi-year campaigns independently of surface shifts. Overcoming communication latency across miles of water remains a technical hurdle. New materials are constantly being developed to survive these crushing forces. But human ingenuity drives the boundaries of what the deep sea will reveal. But we must balance the need for data extraction with ecosystem protection. Modern techniques leave a footprint measured in centimeters, not kilometers. Deep-sea paleontology offers unparalleled fidelity to global environmental shifts. But these deep trenches are the planet's ultimate time capsule archives. The history of plate tectonics and oceanic crust formation awaits discovery here. Understanding crust dynamics impacts our comprehension of terrestrial evolution entirely. A high-bandwidth data streaming enables global, instantaneous analysis collaboration. This global network accelerates the pace of fossil-based scientific breakthroughs. Complex physical models aid visualization when returning to the deep is impossible. Now, the future lies in seamless integration between remote sensing and physical recovery. But each successful mission expands the known timeline of life on Earth significantly. We are learning how entire planetary systems interconnect through the oceans. But even the smallest structures hold secrets about ancient water chemistry. These tireless robotic explorers are our proxies in the alien world below. Ultimately, understanding the deep sea informs our planet's entire evolutionary narrative. The next great paleontological revolution is not waiting on land, it's waiting deep below.